So in this video I'm going to introduce nuclear chemistry. So the topic of nuclear chemistry involves looking at radioactive substances and how they behave. So in other videos I'll talk more about radioactive decay and half-life. But this video is more of a general introduction into nuclear chemistry. So the definition of radioactivity excuse me, is a nuclei that's unstable. And so all elements on the periodic table, or the vast majority, have unstable or radioactive isotopes. So ranging from hydrogen, which is element number 1, all the way up to some much bigger elements, they all have unstable nuclei. So how unstable they are varies, and how many radioactive isotopes there are also varies too. But we'll learn more about what makes those substances radioactive in a second. But just to go back and review some big ideas from earlier on in the year, we're going to look at the definition of mass number, and this is one convention of representing the atomic number and mass number of an element. So for an element X, any random element, the mass number goes up here and the atomic number goes down here. So mass number, or A, is the number of protons added to the number of neutrons. And the atomic number Z is equal to the number of protons inside the nucleus. So for a stable atom, the number of electrons is equal to the number of protons. But in nuclear chemistry, as the name implies, we're only really focused on what's happening in the nucleus of an atom. So we're only really interested in the protons. Also, very often we'll deal with some nuclei or some substances that are ions that have lost or gained electrons. But for now, we're only really focused on number of neutrons and protons, which is the mass number, and atomic number is number of protons. So this is kind of the unique identifier for a substance, the number of protons that it has in its nucleus. And so if we look at this example, uranium-238, it's an unstable version of uranium. If we look at the number of, or make a ratio of the neutrons to protons, so if we do the math here and subtract the atomic number from the mass number, we're going to get 146. And we know that 92 stands for the number of protons inside the nucleus. This is our ratio, and if we simplify this, I'm going to take some liberties with math here, but just for the sake of this example, it's very roughly 1 proton to 1.5 neutrons. So there's a lot more neutrons than there are protons. But for a lot of smaller elements, that's the ratio is closer to 1 to 1. And so the reason for that is, if you imagine adding more and more protons to a nuclei and it's getting bigger and bigger, you need something to hold those protons, which all have positive charges. You need something to hold those together. And that's the job of the neutrons. They act as the glue. So there's a more complex version, complex explanation about why that is, but just to give you the quick overview, it involves something called strong force. And what happens in between protons and neutrons inside the nuclei of an atom is all to do with these quarks called meson quarks. And what happens is that protons and neutrons, once they're close enough to each other, can lose or gain these smaller particles which make up protons and neutrons. And protons and neutrons can lose or gain them. And it just creates this opposite charge. So the protons and neutrons, even though neutrons are neutral and protons have a positive charge, they can attract each other. So this allows the neutrons to act as a glue. But it's all to do with, this is a strong force. It's one of the main 4 forces of nature. Gravity is another one. Electrostatic force is another. And there's another one which I can't remember. But anyway, it's all to do with the tiny particles that make up protons and neutrons moving in between. Imagine like a ping pong ball going in between two paddles really quickly. The meson quarks are moving from proton to neutron backwards and forwards, so there's this opposite charge that's created, and so the neutrons act as glue. So the big idea of that is that the more protons you have, the more neutrons you need to hold that nuclei together to make it stable. So if you imagine helium has 2 protons and 2 neutrons, so that ratio is 1 to 1. So that's a really, really small nuclei. Compare that to this nuclei, which has 92 protons and 146 neutrons. You need way more neutrons to hold that this isotope of uranium together. And so we can represent that on a graph. If we plotted the number of protons against the number of neutrons, and if the red line just represents the ratio of 1 to 1, this curved line shows you that as you add more protons, you need more neutrons, the graph gradually curves up. So the more protons that you add, the more neutrons you need to hold that nuclei together. And the big idea of that is a strong force, all to do with, remember that the neutrons act as glue, they hold the nuclei together, and that's the big idea there. What we'll look at in the next video is radioactive decay. Once a nuclei gets this big, and in fact this version of uranium is unstable, it's radioactive, and so it doesn't stay together. Even though it's got that many neutrons to hold it together, it doesn't stick together. So what happens is it undergoes decay, and when it does that, a huge amount of energy is released, other particles are created, but basically that nuclei doesn't exist, it doesn't stick together. In class we'll look at the periodic table to help you figure out which elements are radioactive, but remember that all elements, all naturally occurring elements actually have radioactive isotopes. Some of them are very unstable and they last for a tiny fraction of a second. Some of them last for years and years and years, thousands of years. But there are some elements that are just naturally radioactive because the nuclei is so big and unstable. There's not enough neutrons to hold it together. So in the next video I'll talk more about radioactive decay.